Hi everyone, thanks for joining us today for today's webinar, which is Reveal the Hidden Reserves of Strength in Reinforced Concrete Slabs. My name's Tom Pritchard, I'm Principal Engineer here at LimitState, and I'll be introducing you to our first speaker shortly, as well as doing some of the demonstrations and rounding up at the end. Today's webinar will talk a little about how the yield line method can be used to uncover potential reserves of strength in reinforced concrete slabs, and how we've managed to automate that process and incorporate it into a software application, which is the LimitState SLAB. You'll also see it put into practice for a range of example problems. The main section of the webinar is going to run for about 35 to 40 minutes, so until approximately 1:10 UK time, and there'll be time for a few questions at the end, which you can submit at any time via the question functionality that should be present in the webinar interface in front of you. We do always attempt to answer as many questions as we can during the webinars, but given the amount of time available, we don't always manage to get around to all of them, but we will, however, follow up on any unanswered questions after the webinar is finished. If you do have any questions regarding the software, you can always contact us at any time via info@limitstate.com, and we'll be more than happy to answer these in detail for you. So I'd like to introduce you to our speaker today, who is Dr. Matthew Gilbert.
Thanks, Tom, and thanks everyone for joining us on the webinar today. Okay, so first slide I want to show is just a couple of examples. Actually of very simple academic yield line analysis problems. So you can see the yield line patterns on the left, a simple fan mechanism, and a slightly more unusual mechanism on the bottom. These are sorts of mechanisms that you'll find in textbooks that appeared over the last few decades. The big problem with the yield line method has been what happens when the geometry is more complex. The patterns on the right were identified using LimitState SLAB, and you can see those will be very, very difficult to identify by hand. And that's the real benefit of a tool like LimitState SLAB, which has automated systematically the yield line method. And we can now just see, to help visualize what's going on, the modes of response. Okay, so what we're going to cover today, first of all, I'm going to say a few words about LimitState, cover a bit of background to the yield line method, demo the software briefly, and then explain how it works, and also just provide some examples just to demonstrate the accuracy of the method. Tom's then going to come back and provide a more in-depth demonstration of the software, and then we'll wrap up with conclusions and questions. Okay, so first, just a few words about LimitState. We're here to provide engineers with primarily ultimate LimitState analysis and design software, and we're making use of optimization algorithms which other tools don't incorporate. We make sure that the software is robust and well validated, and also easy to use, and just got a very small number of clients shown on the right. So many large companies and also small companies using our software in, I think, 30 countries worldwide. Where do we fit, or where does our software fit? It really sits between hand calculations and automated hand calcs in spreadsheets and simple software applications, and the much more powerful but also potentially cumbersome and time-consuming to use advanced methods, which might be non-linear finite elements, discrete elements, and a whole plethora of other tools. So what we're doing is we're using numerical rigid plastic analysis to allow problems of arbitrary geometry, distribution of material properties, etc., to be solved, and they can be solved very, very quickly in a matter of a few seconds. Because we can change many of the key requirements, it means that we can apply the software to a large number of different application types. Okay, so I mentioned LimitState SLAB is effectively using the yield line method, but automating it. Just to remind those of you who've forgotten, and also just to give you a brief introduction if you're not aware of the yield line method. Basically, it's a direct method of analysing a slab at the point of collapse. So typically what we'll do for doing a hand analysis is we would look at a plan view of a slab, we'd guess the critical yield line pattern, we would typically use a work method, so we'd equate internal work done by yield line rotations to the external work done by applied loads, and then we would calculate the collapse load factor. Or if we were doing a design problem, we would identify the required moment capacity for a given set of loading conditions. Some good things about the yield line method: it's simple, it's direct, you get straight to the collapse load. Big things we'll see is that you can get very economic designs using the method, much more economic than using elastic methods, or from an assessment perspective, you could end up with more realistic assessments of the capacity of a slab. So it might mean that you don't need to strengthen a slab if you're doing a building refurb job, for example. Cons, from a hand point of view, the first one is a big worry. If you choose the incorrect mechanism, then you end up with a non-conservative or unsafe solution. So that's one thing. Second thing, it only considers flexural failure, so it doesn't consider punching failure, for example, and it also doesn't provide any information about the slab prior to collapse. Okay, so just go back a few years, 1990s and 2000s, Middleton and co-workers at the University of Cambridge used the yield line method very successfully to demonstrate that many concrete slabs in bridges had more strength than had been assumed. So what they were able to do was demonstrate that many bridges were actually perfectly okay to carry increased loading, didn't need to be strengthened. So what we see on the screen is the elastic assessment results shown in the red bar and the plastic assessment in green. And here's the target is 40-ton assessment. On the right hand side you can actually see a list or a library of all the different yield line patterns that the software that Middleton and co-workers wrote to do the task in hand. So what they were doing was basically cycling through all these different yield line patterns in order to find the critical one for a particular bridge problem under consideration. Now, it's good, but there's always still a worry because there's 27 mechanisms here. What you don't want to have is a situation where your bridge would actually fail in a different mechanism, say mechanism 28, which this software doesn't identify. So it's good, but it doesn't have hugely wide applicability because of the limited number of mechanisms which can be dealt with. If we think of applications to buildings, again, going back some years, there was a European concrete building project. There was basically a building constructed in the Cardington airship hangar in the UK. And what that project found, amongst other things, was that yield line design led to highly economic slabs. So in terms of the weight of steel required for each floor, that was lower than that identified with other methods, and also able to identify simple patterns of reinforcement. So the bar marks per floor indicates, the complexity of the reinforcement. So 22 is a relatively low number. So this indicated the real promise of applying yield line method to design. The big caveat being that it was at the time a hand process. In terms of buildings, then they often have quite irregular slab shapes, particularly compared with bridge decks. So the potential of an automated method to find hidden reserves of strength in an existing structure is clear. So if we've got a building which had a particular use and we want a change of use, what we want to use are methods of analysis which can identify the full reserves of strength, so we don't have to do expensive strengthening works. The other thing is, I mentioned earlier that the yield line method doesn't deal with deflections. It doesn't provide an indication of deflections. But if you're looking for a strengthening refurb job, then actually you can potentially perform load tests on your building to check that the deflections are within reasonable limits. Okay, so what I'm going to do now is just start up the software and just show you how quickly and easy it is to set up a problem. And actually what I'm going to do is I'm going to start with an empty project, which is basically just a sort of blank piece of paper, although you can identify the dimensions of the piece of paper, and it's going to allow me to actually set up something from scratch. And I can use a simple CAD interface in the software to identify the geometry of my slab. So I'll do that now. Clearly, if you've got a CAD drawing with often a much more complex geometry than the one I'm going to just sketch out now, you can read that in as well. So this is one option. You may want to instead use the CAD import function. But I've got a geometry for my slab now, and what I need to do is to identify what the support conditions are. So what I can do is I can select everything and then highlight the boundaries, and then I can choose the support type. So I'm going to choose those to be, for example, simple supports. I also need to tell the software what reinforcement I have, what the definition of the slab is. I'm actually just going to use an inbuilt one here just for simplicity and just drag that on. This is unit MP, so it's got plastic moment resistance of 1, and also it's weightless. And then lastly, I just need to apply some load. I can apply a point load, a line load, or I can just apply a pressure load, a uniform pressure load to the whole thing, which is what I'll do. And that's now should be ready to solve. If I click this green button, then basically it's doing the analysis now, and I can, if necessary, if I want to, I can actually visualize that. And you can see the mechanism. It's interesting mechanism. It's not necessarily one that you would have likely to have identified by hand. In terms of the number in the output box, the solution is 7.2. This is actually an adequacy factor or a multiplier on the applied loading, and I had a unit load on here, and so it's saying I need to multiply up that unit load by 7.2 in order to cause collapse. Now, if I was doing this by hand, then I would probably only be able to consider a limited number of scenarios, because every scenario that you consider, you've got to spend a lot of time looking for the particular mechanism that you think is going to be critical. Here, you're kind of liberated. So what you can do instead is, for example, ring the changes. I can, for example, say, actually, what if I didn't need to actually support this edge of the slab? So change that to be free, for example. How would that affect the mode of response? There's a slight change to the pattern, but only a very small change to the solution. And similarly, I could change these ones also to be free, Just intuitively, I would expect there to be a greater impact on the capacity of the structures, but let's just check that. So actually it's gone from 7.2 to 6.97 right down to 2.09. So you can see that, as you might expect, in that case we have a very serious impact on the capacity. So that gives you a little flavour of using the software. Tom will provide you with a significantly more in-depth walk through the software shortly. But the main thing I wanted to get across is how sort of quick and simple it is to get going with the software. So big question is, how does it actually work? Actually some theory developed relatively recently. The technology is called discontinuity layout optimization, bit of a mouthful, or DLO for short. Basically what we're doing is we are starting with a slab with boundary conditions, populating that slab with nodes, interconnecting those nodes with potential yield lines, and then using optimization, and in this case linear optimization, which is quick and efficient, to identify the critical yield line pattern. In terms of the mathematics, basically what we're doing is we're finding the minimum energy solution for the problem, subject to a unit displacement constraint using the principle of virtual work and nodal compatibility constraints. And the nodal compatibility is kind of the key to it. If we have a look at a particular node in a problem, so here we've got a node in the bottom corner, the nodal compatibility constraint requires that if we basically track round the node and we resolve the rotations in the x direction first and then the y direction, then the sum of those rotations must equal 0. And this is actually taken from an article in the October 15 issue of the Structural Engineer, which provides a more accessible description of how the DLO process works than in the original 2014 paper. Okay, just a few examples just to show you how it works in terms of accuracy. So for a simple square slab problem, simple supports, then effectively we get the exact solution without any difficulty at all. We can pick up the corner levers that you get when you have fixed supports and slabs with top and bottom reinforcement. And also if we have a point load, we also get a fan mechanism and very close approximation to the exact solution. Something more complicated from the literature. This is a slab with a hole, and we get actually it doesn't say the load factor, but it's a better solution than any other workers in the literature have managed to identify. Moving on to an apartment. This was actually a problem that was dealt with in the 2004 concrete sensor guide on yield line design, and they actually documented the design of a highly irregular floor slab for that apartment block that you just saw, and they used a whole variety of different potential failure mechanisms to identify what the critical would be and hence design accordingly. The one that they found to be most critical was actually the one on the left-hand side, is folding plate mechanism, and actually it's very similar to the mechanism that you can see that the software LimitState slab identified. Okay, so I didn't have any numbers on some of these, but in this particular one case, we were, I think, 7%. We identified a a capacity which was 7% lower than that predicted using the hand method. So actually the hand method was pretty good in that case. For the previous cases, you can see in, for example, the 2014 paper that we can get to within a very, very small fraction of 1% agreement with analytical solutions. So we're talking about, you know, in a second or so getting within 1%. If you wait a bit longer, you can get to, you know, 0.02 or 3% away from the analytical solution. Okay, so I'm now going to pass over to Tom, who's just going to move on to the more in-depth demonstration of the LimitState SLAB software.
Thank you, Matthew. So I'm just going to take a quick look around the software interface just before we go on to looking at some of the examples. So we can see here that it's actually a sort of very simple piece of software to use with structural definitions on the left hand here, so basically materials, and on the right hand side we have what's called a property editor. So if we select anything, and I'll just use Matthew's example here, if we select a part of the structure, then on the right hand side we can see in the property editor all of the properties of that, in this particular case solid, are displayed on the left hand side here, including what the structural definition is and what the nodal spacing is around it and what the geometry is at the bottom there. So that just to give you a quick flavour of how the software is displaying some of the things. We'll go on to looking at the wizards, which are potentially the first entry point into the software. So if we create a new project, we can see here that we have an option to start with an empty project like Matthew had demonstrated earlier, and we also have the options to do a rectangular slab or a rectangular slab with a hole. I'm just going to choose a rectangular slab for this case, and we can see that we come onto this dialog here which has a number of different steps within it, so project settings, geometry settings, structural definitions, loads, and so on. For the project we don't actually need to enter anything, so we'll go on to the interesting part, which is the geometry, and you can see it's set up to allow you to do very quickly a rectangular slab and also with the capability to add a skew into it. In this case what we're going to do is look at a slab where we have simple supports all the way around. I'll leave the width and the height as they are and not add any skew into it, so it's basically a 5x4 rectangle with simple supports all the way around. The next stage is to add a structural definition or a material to this particular slab. Here what we're going to do is just make a new one, so I'll set the colour, make it a bluish colour just to differentiate it from some of the others in there, and we can see here on the right hand side that we have properties, and the only properties that we need to assign to any of the materials in the problem here are MP values for hogging and sagging, and then an angle at which the moment actually acts. So you can see it's basically perpendicular to the reinforcement, so if the reinforcement is at 15 degrees skew, then you just enter an angle of 105 into that field there and it will act appropriately. So for this case all we're going to do is keep it as an isotropic material, so everything as 1. I'm just going to set thickness and unit weight to 0 just to make it a bit simpler for us to look at, but you can obviously enter your own values for that. So move on to the loading, and you can see again we have a separate tab with partial safety factors and loads that we're adding to them. So in our solve, what we're looking at is a number of different scenarios where we have combinations of partial safety factors and loading that is applied to the slab, and we can do 2, 3, 4, however many we want of those at one time, and the software will come out with the critical case and show that to you at the end. Again, all we're going to do here is look at the case with a simple pressure load that is applied over the entire structure there. So if I just click change, you can see here that the whole rectangle is selected and has a pressure load applied to it. And then finally, the analysis tab, we've got a nodal density of medium, and if you were sort of listening earlier when Matthew was explaining how the software actually works in the background, we can change the nodal density according to the type of problem that we're sort of looking at, whether we're doing a scoping exercise or whether we're wanting to look in some quite fine detail. I'm just going to leave it on medium, which is a target number of 500 nodes to cover the entire slab for this particular problem. And I click finish. We can see here we have our problem set up. We have the simple supports around the outside, and if I click on here you can see that the loading is applied to the entire slab, and then I can just click solve, and the software goes through a number of different possibilities until it finally finishes on this envelope type mechanism, which is obviously something that should be quite familiar from textbooks and things like that. So what I can do now is we can see the load factor here is 1.22, which is basically saying that we can increase our unit pressure load by 1.22 in order to cause collapse. We can also animate the failure mechanism to see the way in which it is failing, and also if I click on analysis and then report, you see there's a few options here. I can click OK and get a report that outputs all the pertinent information about that problem, including a picture of the failure mechanism and the adequacy factor here, so that you can then either use it yourself or pass it on to clients, that sort of thing. But the main thing about LimitState SLAB is the way in which you can very quickly make changes to the problem and potentially do sort of investigative what-if type analysis. So we're going to start with this particular slab and we'll just make some changes to it and see what happens. So the first thing is that we had an isotropic material to start with. I want to know maybe what happens if I make that orthotropic. So for the first rebar direction, we're just going to change the MP value to 5 rather than 1. Solve again and see what happens. And we can see again the software very quickly homes in on an envelope type failure mechanism, but in this case the sort of central horizontal yield line across the middle is a lot longer than it was in the previous case, and that's something that we would potentially expect from having increased this value here. So if I reset it, it's just asking me whether I want to unlock it, so it's doing a bit of a sense check. If I set it back to an isotropic material, maybe another thing that we want to do is add a column to this particular problem. So if I draw myself a little square there, all we need to do to add a column into it is to delete that section, and then for all of the boundaries around the outside, the external boundaries there, if I set them to be fixed, we can see now we've got a column in the center of the slab, or slightly to the left of the center of the slab, and I can solve. And what we can see here is a very different failure mechanism. So what we've got is a fan type mechanism around the column, but then also combined with a sort of slightly modified envelope around that towards the edges. And our adequacy factor has gone from 3.7 to 2.9, sorry. So we can see very quickly what the changes in boundary conditions and things like that will actually, how it will affect that particular problem. So maybe another thing that we want to do, if I turn off the grid, is to say, okay, what's the adequacy factor if that right hand side isn't supported at all? So I can click solve on there, and we've had quite a dramatic change in the critical failure mechanism. So we've gone from having a fan around the column and the sort of envelope type mechanism to having this fan that's attracted towards the free edge to the right hand side of the column, and the adequacy factor has gone down quite considerably, so pretty much halved just by removing the support from that side. So maybe what we want to do in this particular case would be to add another column. So if I draw one in there, again it's just a very simple case of drawing myself a rectangle and then adding support around the outsides of it. We can see what happens in this particular case. And now we're going back to the type of failure mechanism that we saw before, so with the fan mechanism around the columns and then this sort of modified envelope failure mechanism again, and again the adequacy factor has gone up from 1.5 to 2.88. So that's quite a quick look at what you can do in order to make things, make alterations in your models in LimitState SLAB, and how quick it is to actually solve those. What we're going to do now is look at a slightly more complex geometry. So what we can do with the software is import both what we call geometries and structural definitions. So if I go to import geometry, I'm not going to save this problem. What we've got is a DXF file that we've already prepared outside of the software in whichever CAD software that we have available. If I click OK to import that, you can see that what's happened is that the software has identified closed loops within that DXF file and made solids within LimitState SLAB that we can then select and assign material properties and such like to. So what we've got here is our apartment floor. What we also want to do is to be able to assign materials to it. So if I import structural definitions into there, you can see that we've got a CSV file that we can open, and 7 structural definitions have been imported. So we can set that up very quickly, and it means that we can make relatively complex models quite quickly within the software. So then it's just a case of taking the different parts of the structure. So maybe these are our main floors. We have kitchens here, just drag and drop, assigning these structural definitions to them. We have balconies on the edges, and maybe our stairwells are these two here. And we can go through and set those things accordingly. Again, as previously, what we can also do is click on these icons up here, and we can add loads to different solids. So I can say select all of them, click OK, and apply, in this case, a unit pressure to them, and it will do that around all of the solids that exist within the software. And once we've done that, and once we have set up our boundary conditions, then we can solve the problem. So I'm not going to go through it again, but basically our slab here is supported on all of these internal columns with no external support around it at all. What I can do is just open a version of the software, a version of the model, sorry, that we have already saved. So we can see here we have our main floor, we have our isotropic material that is applied to it, and so on. And if we click solve, again, very, very quickly, the software goes through a number of different potential failure mechanisms and then homes in on the one that's critical. And we can see here it's isolated to the top left-hand corner of the apartment floor, and we can animate it to see how that would actually look in real life. So that's a very quick look at how we can put in complex geometries into the software and solve them using DXF and also predetermined material properties with a CSV file, and also, as we've seen prior to that, we have the ability to very quickly generate and make changes to sort of simpler geometries without having to go outside of the software. So if I go back to the PowerPoint, just go through some of the conclusions before we go on to any questions. So what we have seen is that the yield line method is a good way of finding potential extra capacity that you may not have known about within your slab, and that LimitState SLAB has systematically automated that for sort of the first time in a software application, and that the software is easy to use and should hopefully be able to give you a good idea of what happens if situations change, or maybe what happens if you need to make some remediation measures to your model. So we've got a few minutes that are available now for questions, so if you do have any, then please just use the question interface in front of you and we will get round to answering them for you. Okay, so we've had one question, which is does the software work for bridges as well as floor slabs, and can you specify moving loads rather than just static ones? So the answer to that is yes, and if you bear with me, what I can do is just open up the software again and I will open a different one. So we've got a bridge deck example here, where the loading, if we have a look at it, you can see here it was a little too involved to go into in any detail during the webinar, but it will be the subject of another one at some point, so using LimitState Slabs specifically for bridges. But we can see here that what we've done is specify just 4 point loads, and we can step through, and it's very easy to move those point loads across the slab and find the critical mechanism and the critical load case based upon that. Let's see if we have any more questions. Okay, so we've had a question, do we need to calculate the plastic moment capacity first and then use this in the input to check the adequacy factor? So the answer to that is yes, the software does require you to have the MP values in advance, but we're looking at streamlining this for future versions of the software. So a quick look through. Okay, so we've had one more question. So if the slab thickness is different in different areas, how does this work within the software? So actually this is probably quite a good example to keep on the screen. So if I look here, we can see that our beam sections in the bridge here have a thickness of 0.2 meters and a unit weight of 24, whereas our deck has a thickness of 4 and a unit weight of 24. So you can specify different parts of the structure, and then the thickness of it is applied using these structural definitions. So if you have 3 or 4 different thicknesses of slab within one model, then you just specify 3 or 4 different structural definitions and apply those accordingly, and the software will use that in its calculations, especially if you're using the unit weight, not the unit weight, the self weight of the slab as part of the loading, then that will be then taken into account. So that thickness and that unit weight will be used in order to determine what the self weight of the slab in that area is. Okay, so I think that's it for the questions. So I'd just like to do a quick roundup. So I'd like to thank Matthew for his part of the presentation, and thank everybody who has joined us today. We do hope you found the webinar informative. And if you aren't current users of the software, then we'll try and get in touch with you over the next few days just to find out if you have any further questions that may have come up after the webinar is finished. And as mentioned, if anybody does have any questions and they want to get in contact with us, then please do send us an email on info@limitstate.com and we'll get back to you as soon as possible. As I mentioned briefly, you may be interested to know that we'll have a number of webinars over the year that cover all the LimitState product range, and one of them is likely to be the use of LimitState Slab for bridges. And in general they will focus more on particular problem types and applications. So please do look out for the event notifications that we'll send out to you. Generally these go out via email, and they're also posted on our website at limitstate.com/events, and we do occasionally post in LinkedIn as well. So I think that's it for the webinar. Thank you all for taking the time to join us, and we do hope to speak to you again in one of our future sessions. So thanks and goodbye.